All right, so like I mentioned last Friday, I'm going to be gone on Wednesday and Friday, so this is our last meeting until 2 weeks from now. It would be easy to forget a lot of stuff between now and then, so I would encourage you strongly to continue studying, reading the book. I will assign some problems that technically are not due until after you come back from spring break, but I would encourage you to work on them maybe slowly over the week, so you just sort of are thinking about this stuff as much as possible to keep it as fresh in your mind as you can. I'm probably going to suggest a couple of videos that I found a few videos online that talk about, especially the ideas in chapter 7 about cosets and Lagrange's theorem. We will touch on that today. But I think mostly it's going to end up being still continuing to be about chapter 6, focus in lecture 14a on what it means to show two groups are not isomorphic. Something called Cayley's theorem, automorphisms and inner automorphisms, stuff you've read about, but it's kind of abstract and maybe confusing. We'll solidify it somewhat today, but you'll want to continue thinking about it. I will discuss it more after spring break, probably focusing on examples after spring break. Today is probably going to be more of a big idea kind of day. That'll probably continue into lecture 14b, and then again, cosets and Lagrange's theorem. We'll spend some time with that too. This stuff is starting now, I think, to get kind of, well, you might call it strange. I think the idea of an isomorphism, an automorphism, an inner automorphism. And then as you start reading chapter 7, as you should have by now, cosets, all these things are kind of strange, but remember what our goals are. We are mathematical taxonomists in this class. Our main goals, at least for right now, are study a wide variety of different groups and their various properties, especially noting the similarities and differences. We want to classify things. We will also, in about a month or so, maybe a little bit more than a month because of spring break, I'm not sure, start talking about some other algebraic structures, rings and fields, especially. And we'll try to do similar kinds of things with those. Actually, our main applications that I hinted at the first few days of class will come with rings and fields. We'll be talking about how the theory of rings and fields enriches our knowledge of how to factor polynomials. Again, not a real exciting application perhaps, but it is an application nonetheless, and it is historical. And part of that classification is to determine how isomorphism classes might depend on the order of the group. This is perhaps the most interesting thing I think we can consider. We're not going to be able to prove everything related to that, but we'll talk about it and perhaps prove some things related to that. In fact, we've already done that a little bit. I've mentioned that any group of prime order must be cyclic. I mentioned that. So that's one example of a classification theorem, how the isomorphism class depends on the order of the group. And remember, a cyclic group of finite order, say ZP where P is a prime, well, say of order P where P is a prime, is going to be isomorphic to ZP, our standard cyclic group of order P. All right, so we talked a lot about what the definition of an isomorphism is and the examples of isomorphisms and their properties, but we should emphasize what are some ways to show two groups are not isomorphic. The easiest way is to show they have different orders. Okay, if they both happen to be finite groups and the order of the group, the number of elements in one group is different than the other, then they're not going to be isomorphic. Isomorphisms, besides being operation preserving, are one-to-one and onto. And that means that the domain and the codomain are going to have the same cardinality is the official word for number of elements. If it's finite, that's easy. If it's infinite, it gets a bit harder, unless you're comparing it with a finite group. Certainly any infinite group is not isomorphic to any finite group. If you're comparing two infinite groups, however, like say the integers versus the rationals versus the reals versus the complex numbers, under addition I'm talking about, they all have infinite order. Actually, it gets a little bit more strange than that. There are different sizes of infinity, and you'll probably learn about that a little bit in real analysis. The infinity of the rationals, for example, the reals and the complex numbers is somehow higher than the infinity of the irrationals and the integers. I'm not going to get into that, but that's just something to be aware of. You can also show that one group is cyclic and the other's not. Then they can't be isomorphic, right? Because if one group is cyclic and you've got an isomorphism from that group to another one, that other group has to be cyclic. We talked about that. Show that one group is Abelian and the other one is not. First three are pretty easy. It gets a little tougher as you continue going down. Show that the largest order of any element in the first group is different than the largest order of any element in the other. Maybe the groups have the same orders. Maybe they're both not cyclic, say. And maybe they're both not Abelian, for example. But you still, based on these three bullets, don't know whether they're isomorphic or not. Well, you could compute orders of elements. Maybe the overall groups have order 60, like A5 does. Right, the alternating group of degree 5 has order 5 factorial over 2. Should be 60. The order of A5. Maybe you got A5 and you got some other group of order 60. Definitely not cyclic, definitely not Abelian. You could try computing the orders of the elements, and maybe, in one group you find the highest order of an element is 30, and the other one you find it to be 50. I'm not going to get into A5 itself here, but that kind of thing could happen. That means they can't be isomorphic, because isomorphisms have to preserve orders. Maybe they both have, as their elements of highest order 30. Well, how many elements have order 30 in both groups? Maybe that number is different. And these kinds of thoughts can distinguish between, for example, these three groups. Why are no two of Z12, D6, that would be the symmetries of a regular hexagon, and A4 isomorphic? Well, certainly Z12 is cyclic and Abelian, whereas these two are not. That's easy. But how do you distinguish between these two, D6 and A4? Can you think of a way offhand to distinguish between those two? Think in terms of the orders of elements and maybe having certain cyclic subgroups versus not. What's the rotation, the non-identity rotation in here that's going to have the smallest angle in D6? Symmetries of a regular hexagon. 60 degrees. R60 is going to be an element of D6 of order 6. Does A4 have any elements of order 6? That kind of thing would have order 2, and it is an even permutation. It's an A4. That's a 3 cycle. Remember, 3 cycles are even permutations. That has order 3. The only way you're going to get an element of order 6 in A4 would be as if you had disjoint cycles, one of length 3 and the other of length 2, or a 6 cycle. But we don't have enough elements to permute. Right? These are permuting 4 objects, 1, 2, 3, and 4. There's no way you're going to get an element of order 6 in A4. There you go. D6 and A4 not isomorphic. Okay. And you could continue thinking about the number of elements of various orders as well. You would see that they're not isomorphic. In general, it's easier to show two groups are not isomorphic than to show they are isomorphic, even if they do happen to be isomorphic. Just doing these things and seeing that the orders, for example, all match is not enough to show they are isomorphic. You have to come up with an isomorphism, and that could be difficult. So in general, this is easier. All right, on to Cayley's theorem and regular representations of groups. Here's what Cayley's theorem says. Every group is isomorphic to a group of permutations. No matter what group you have, no matter whether it's finite or infinite, it's isomorphic to some group of permutations. What's the significance of that? It does say that studying groups of permutations is equivalent, at least logically speaking, to studying groups in the abstract. All the different kinds of behaviors that can occur with groups in the abstract are going to occur with groups of permutations. course, if we were only studying permutations, we'd lose some of the richness of the theory. By doing the abstract theory, we see its applications more readily to other areas of math, including, for example, thinking about matrices. We talked about GL, the general linear group of 2 by 2 matrices with real entries, or entries, say, from Z5, for example. And we're thinking of those elements as being actual matrices, and the operation as being matrix multiplication, and all that entails as far as applications, for example, to things in linear algebra. You know, linear algebra's got plenty of applications. So if we were only thinking about groups of permutations, never thinking about other kinds of groups, then we would lose some of the richness again as far as seeing connections between different subjects and seeing possible points of application. But as far as the abstract stuff goes, as far as the logic goes, we could prove everything there is to prove about groups in the abstract in the context of permutation groups. I guess you could say it does provide a concrete example in every situation if you need one for some reason. What's the idea of the proof? I'm not going to go through the proof in detail, but what's the idea? You're given a group G. Given a group G. You have to come up with a group of permutations that this is isomorphic to. How in the world are you going to do this in the abstract? You don't know what G is. If you're going to prove an abstract theorem like this, you somehow have to use G. And you know, Cayley, evidently the first person who thought of this, probably had to think long and hard about it. How in the world could I come up with a group that's going to be isomorphic to G, that's going to happen to be elements that are permutations? And so here's the idea. Given little g and capital G, you can use that to create a permutation. We can define, the permutation is called T sub G. It is going to be a permutation on what set? Permutations are one-to-one and onto functions. Careful, they're not isomorphisms, they're just one-to-one and onto functions. From a set to itself, right? S5, the elements are permutations of this set. You're mapping those objects to themselves. The permutation here is going to map the set G to itself. G is a group, but it's also a set. I can consider the group of permutations, all permutations on G. What kind of formula? Here's the formula. For an arbitrary x in G, this is in capital G, define T sub G of x to be G times x. It's like a linear function. Is it a permutation of G? It does certainly map G to itself by closure, right? Give me any element of capital G I could plug into this function. Little g times that element of capital G is still going to be in capital G. So it is certainly a function from G to itself. Is it one-to-one and onto? If this were true, T sub G of x equal T sub G of y, by the formula for T sub G, that would imply Gx equals Gy. And then I can include x equals y. What's the reason? What's the reason for that last step?
Cancellation law.
Cancellation law, left cancellation, okay? Again, I won't mark it wrong if you put the slashes through the g's. Don't put divided by g, don't do that. Because again, groups are not abelian in general. You could certainly show your work by multiplying on the left both sides by G inverse. Or you could just say by the cancellation law. Go from here to here. So that would verify that T sub G is one-to-one. is it onto? Given y in capital G, how should I choose x so that x gets mapped to y? I want to choose x so t sub g of x is y, i.e. g times x is y, which would be equivalent to x being g inverse y. Right? Solving the linear equation for the unknown, essentially. Technically, your argument would be then t sub g of g inverse y. If you want to be extra picky about steps, you could include the step where you use the associative law and the step where that equals the identity before writing the output. Now we're going to verify t sub g is on. Verifying t sub g is a permutation. Not an isomorphism. I don't have to verify operation preserving. That's not what we're talking about here. It's just got to be one-to-one and onto from G to itself. It's a permutation. Okay, so that's all fine and good, but are we done? Is that enough to verify that G is going to be isomorphic to what? Wait a minute. What in the world am I doing? What's the value of this? I haven't said what G will end up being isomorphic to yet. Anybody see where this is going? What am I doing here? What's this about? What's going to be the group that G is going to be isomorphic to? That's a permutation. Where's the group? Remember from the reading even? It'll be the collection of all t sub g's as little g varies over capital G under function composition. A group of permutations. Not just permutations themselves as a set, but with an operation, function composition. Let G bar be the set of all such t sub g as g little g ranges over capital G under the operation of function composition. Wait a minute, is this definitely a group? That should be figured out as well before we even bother try to show that they're isomorphic. How do you multiply two elements in the group? Well, you compose them. That's the multiplication. So t sub g composed with t sub h. But what does it equal? Is it something of the same form? You really do need to verify that. Is the composition of these two t's equal, I'll put a question mark here, to some t sub question mark? You can certainly compose them, but do you get another element of the same form? So it's really in the same collection. Closure does need to be verified here. Take an arbitrary element x, plug it into t sub h, get hx, plug that into t sub g, get g times in parentheses hx. But wait a minute, the associative law says that's gh times x, and that's the same as t sub gh of x. That does need to be verified. That you do get something of the same form, a t sub something. What's the identity? What do you think the identity is? T sub, take a guess. What's the only thing you can guess? That would make sense to guess. Yeah, T sub E, where the E is the identity of G. The identity function maps everything to itself. And it is the T sub E is the identity of this group of permutations. Because I can write that this. It is important here to distinguish between a function and its outputs. You know, when you write things like this, that's really talking about the outputs of the function, which are elements of capital G. When I write this kind of thing, I'm really talking about the elements of this new group, G bar. I don't want to put the x's here. These are the functions themselves. These are their outputs. We don't always make such a subtle distinction in most math classes. Technically, it is important to make. It usually doesn't cause confusion in most classes. And what's the inverse of an element? T sub G, it would be T sub G inverse. And this calculation verifies it, and you don't even need to bother putting any of x's. Because we've already seen that in general, T sub G composed with T sub H is the same as T sub GH. Are we done? No, we're still not done. What's the relevant isomorphism? What have we done so far? What have I mentioned here? I said how to define G bar, that is the candidate group, to be isomorphic to G, and verified that it is a group because this key equation right there, that itself needs to be verified. But how do you know it's isomorphic to G? What's the isomorphism? You got a map. You need a phi function, right? An isomorphism from G to G bar. Mapping an arbitrary element of capital G onto an element of G bar. What's the only thing you could possibly guess? Just follow your nose. What's the only thing you could possibly guess here? As an element of G bar you want this to map to?
GX.
Here's a hint. T sub G. It's the only thing that makes sense worth trying. It's not obvious that this is an isomorphism. It's the only thing you could possibly try, though, that makes any sense to try. And fortunately, it is an isomorphism. For example, it is operation preserving. Once again, because of the key equation, that T sub GH would be T sub G composed with T sub H. And this is the same as phi of G composed with phi of H. The T's are functions. The phi is a function. The G and H are not functions, at least a priori. They're just arbitrary elements of an arbitrary group, G. This right there, that's a composition of two functions. It's not. It's a product in G bar, but in reality, it's a composition of functions. There's TG composed with TH. Strange. Takes some getting used to. So there's the relevant isomorphism. You'd have to verify it's one-to-one and onto as well, but that's not too bad. Right? This class continues to stay strange like this, okay? At least with groups especially. Maybe with rings and fields at first, at least, it feels a little bit more concrete. Because we're talking a lot about polynomials, for example. But here in this, the rest of the group theory stuff, it continues to stay strange. But what are we doing? We're mathematical taxonomists. We're trying to build up tools that can help us do this classification stuff. And it's not clear how this kind of stuff might be helpful. That's sometimes the case when you're doing math. It's not clear where you're going. You just continue going and see what happens sometimes. The group of permutations G bar defined in the previous slide is called the left regular representation of G. There's an analogous concept of a right regular representation of G. We could define T sub G instead by this formula, multiplied by G on the right instead of on the left. Technically speaking, if G is not abelian, this is a different kind of function than the left one, where G was on the left. G is abelian, it's going to be the same function, same permutation. But evidently, G would still be isomorphic to G bar, where you create G bar to be the collection of these things. And you get the right regular representation of G. This is sort of the foundation of something called representation theory, which got sort of its own big sub-theory of group theory. Has lots of applications in physics, for example. We're not really going to get into it beyond what we're just saying here. As an example, we could represent the left regular representation of D3 of various elements in disjoint cycle form, which brings up actually a typo in the book that I found. Didn't notice until this morning, actually. I wasn't reading it carefully enough. If you got your book, it'd be good to open up to page 125. Maybe you noticed this example and you thought maybe that was a typo, but you thought, no, the author couldn't possibly make a mistake. No, authors make mistakes, just like I do. They don't always catch their mistakes. Page 125, example 8, smack dab in the middle of the page. The left regular representation of TR270 is incorrect. I'll tell you how to correct it here in a second, but let's just do the example here. So here's a Cayley table for D3. Symmetries of an equilateral triangle. Group with 6 elements. 3 rotations. Although one of the rotations is really just the identity map, so you wouldn't have to think of it as a rotation. You go ahead and write it as R0 anyway, and the 3 flips V, D, and D prime. V being a reflection across the vertical axis of symmetry. D being a reflection across this diagonal, and D prime being a reflection across that diagonal. I could ask, for example, what is T sub R120? And how would you represent this permutation? Maybe in the cycle notation. That's what we're after here. It is a permutation on a finite set. So we could represent it in cycle notation. Well, let's first figure out what its outputs are for the various inputs. We are multiplying by R120 on the left. So when I apply it to R0, I get R120. When I apply it to R120, I get R240. When I apply it to R240, I get the identity R0. When I apply it to V, what do I get? I better look at the table. I got to do R120 times V, start R120 with R120 on the left here, go to under V, I get D. Apply it to D, I'm going to get D prime. Apply it to D prime, I'm going to get B. Okay, so this is a permutation. It's mapping R0 to R120, R120 to R240, R240 back to R0. That forms a cycle. With cycle notation, I could write this. And what happens with the flips? It maps V to D, D to D prime to V. I could write this. This is cycle notation, just like in chapter 5. Those are disjoint cycles. Each of length 3. This element in G bar TR120 has order 3. You get this? It's mapping R0 to R120 because of that equation. It maps R120 to R240 because of this equation. It maps R240 back to R0 because of this one. It maps V to D, D to D prime, and D prime back to V. So this could be a way you could represent this as a cycle, or product of disjoint cycles in this case. And I could do this not just for R120, but I could also do it for the other elements. To get G bar, and G bar is going to have then 6 elements, and if you think about it, based on this representations, this is really a subgroup of S6. Because we've got 6 objects that we're permuting. The elements of G itself, T3. Does that make sense? Can I clarify anything there? And I could continue. Now what's the typo? In example 8, TR270, the first 2 things are incorrect. The author wrote R0, R270, R90, R0. That's what it says in my book. Does it say that in yours? That's incorrect. When you multiply in D4, symmetries of square, by R270 on the left, when you multiply R270 by itself, you don't get back to the identity. You get R180. And when you multiply R180 by R270, you get R90. And when you multiply R90 by R270, you get back to the identity. This should really have been written like this. It's really a 4 cycle for that part of the representation of this permutation in disjoint cycle form. I mean, you should have known it's a typo right away because it's a disjoint cycle form, and the way the book has it, the R0 appears twice in 2 different cycles. So it had to be a typo. Okay? So if you caught that, then that was good. Okay? It shows you're really thinking about things carefully. All right, let's take our quiz.